we'll be having 3 more lectures, okay, after this today's lecture. So November 5th is the last date for of instructions. Okay. Afterwards, exams will start and some examinations. So anyhow, I think this course does not have written and some examination. I hope all of you are aware of it. And other thing, there is a due for assignment and also due for term paper. I presume that all of you already worked on term paper. Am I right?
Yes, sir. We are working.
Term, pa- term paper report. Working or worked already?
Sir, working, sir.
Working. Okay. See, one thing actually I wanted to, I think what I mentioned in my first day lecture slide, on 30th onwards, presentations and YOs will be conducted. Okay. All of you are ready for 30th? All of you are ready for that, okay, for YOs and term paper presentation?
Yes, sir. Yes, sir.
Will be ready? Okay.
Sir, one question here.
Hmm.
Is there anything different you are expecting in the term paper presentation as compared to the term paper report, or it's more or less the same only?
More or less same. How much you understood? Okay, that is okay.
Yeah, I mean, all those details are there in the term paper report. We just have to make it in the
Present.
form of a presentation.
Yeah. So how you are
Nothing extra,
communicating?
like.
Yes, yes. How we are communicating? Okay.
Okay,
Whatever you understood from the given paper and how much, okay, connecting
okay, okay,
with the whatever you learned, okay, from the lecture slides, whatever. Okay. I
okay,
wanted to
okay.
see how you are connecting. Okay. So you are
Yes, sir.
understanding what you gained in this course
Yes.
and how you are actually how much understood from the paper. Okay. Okay. So shall I float an Excel sheet to take the timings from you for 30th, or would you like to have some other day presentations and hours? Choice is okay because I said 30th onwards. Okay, so I'll be having till time 20th of November to complete the course requirements. Okay, so if, if you want to have it on 30th, I can conduct entire 30th the whole Saturday, or if you want to have some more time to read, okay, bios basically from the course syllabus. Okay, term paper is actually will be having 15 minutes, okay, followed by 15 minutes for two students, so half an hour per okay, two students.
Sir, so for the Viva, the portion you teach till today uh, will be there,
Y-
right?
yeah, yeah, so if you want to have it on 30th till, okay, Friday, whatever I teach till Friday. Okay,
Okay, okay.
okay, if you
And
want
you
to,
told that there is an assignment. I couldn't see any assignment three.
But it was already
You told
submitted,
at
sir,
the start.
assignment. It was the 21st, last date for submitting assignment. So before this,
no, no,
everyone is submitted,
yeah,
I think.
only two assignment, no,
Yes,
how
sir,
many
yes, sir.
assignments are,
Actually, sir,
two
you
assignments.
in that starting
Oh,
of the
okay,
class, you are
okay.
telling there is a bending of assignment also like that.
Okay. Yeah, before quiz actually, yeah, that was
Please
the
submit
deadline.
also.
Yeah. Yes, yes. Yeah.
Sir, actually, yeah, we have actually those who are want to done on 30, they have to, sir. But if we have any extra time, we can do on some other day.
No, that's what
So,
I'm telling. We have time from, okay, 30th of this month to 20th of November.
okay, sir.
Okay. So now if you want to have it some other, okay, days, also fine with me. Okay?
Okay, sir.
That's why I said actually in the my first slide I said onwards, okay,
Yes,
30th
sir.
onwards. Okay. See, for example, somebody wants to finish it before, okay, I'm okay with that. Somebody wants to take time, then also it's fine. Okay, it's only between two. Okay, for example, team constituting two students, so those two students will be there, okay, for the half an hour time. So 15 minutes, okay, presentation plus discussion on the term paper. Okay, 12 plus 12 minutes on presentation, 3 minutes on discussion on the term paper. Then 15 minutes on bios, okay, for two students together. That means actually it's a 7 minutes like that it will come. Okay.
Sir, Viva will be there on term paper or on the
No,
course?
term paper only just discussion. That's a different. Okay, bios is an entire syllabus. It is an entire syllabus. Okay, bios is a separate marks. Term paper report has different separate marks. Term paper presentation has different separate marks. Okay, if you see that lecture slides, okay, the first day lecture slides or the evaluation procedure what I used, okay, what I mentioned. If you see term paper report plus presentation, I think together will be having 30 marks and 20 marks viva's examination. Okay.
Hello.
Yes.
Sir, like apart from 30th, what will be the will you tell the other date or how like you are saying onwards? So will you tell the other date?
Because I do not know because when are your exams, okay, will be okay. If you're going to finish it, okay. So that's why I'll float an Excel sheet. Okay. Take your okay time available times. Like I'll give some tentative dates and times. You can fill those, okay, where you are available. Okay. Is it okay or any other means you want to have? Okay. Because I do not know because some of you might be taking some courses, okay, other courses. See, any time is fine because now it's once the semester, the end semester exam starts. Actually, I'm available anytime. Okay, except ninth. Okay, ninth of I think I'll be having my other course examination. Except ninth, so other days I'm available. Okay, we can have a fixed half an hour time for two students.
Sir, so the tentative dates that you give, could we get back to you on that? Like after you give the tentative dates, we could choose
No, that's
maybe
what
if
I
possible.
wanted to see whether you want to somebody, any of you want to have 30th or you want to have after 30th only. Okay, that's what I want to. Just first, that is the first thing.
So
Any
like
of
I want after 30th.
okay, so
I also
so
want after
Sir, I
30th.
also want out.
okay, so what I will do, I'll defer this 30th one. Just if somebody wants, okay, I'll put that. Okay, I'll conduct it. It's not an issue. So what I'll do, I'll give okay some tentative dates. For example, 1/30th. Okay, if somebody wants to have it, okay, it's not okay. I'm available 30th and third day. Then okay, we can have it. Okay, after I think after 9th, 10, 11, 12, 13. Okay, is it okay? 10, 11, 12, 13.
Yes, sir.
Yes, sir. Yes, sir.
Those
Yes, sir.
4 days.
Okay, sir.
Okay.
Yes, sir.
So those 4 days, I think let's have, okay. I think I can have a spread. You can spread it across, okay. So I can available myself those 4 days, okay. So I think I'll put 30th also. Somebody wants to have it because as per whatever I mentioned, we'll have it on 30th also. Somebody wants to have it, okay. Otherwise, we can have it 10 to 13th. Okay. So
Okay, sir.
I could see most of I think students are PhD and senior M.Tech, second year M.Tech students. Okay, I could see. So that way, I think they might not be doing so many courses. Okay, so in that case, it might many of them might not be having regular and some examinations. Okay.
Sir, and the term paper report submission, is that date also going to change or it
No, no,
shall
no.
remain?
That is fixed. That is fixed. Okay. I
Okay,
said so if you
okay,
see that I said actually presentations 30th onwards. Okay.
okay, okay, sir. Okay,
This is these those dates are fixed. Okay. Already Moodle everything has been okay set. The time has been set.
okay, sir. Okay.
Okay. Is it okay? I think okay. Let's I think
Yes, sir.
Yes, sir.
if
It is
any
fine.
yeah if any other things are there, that's fine. Let me know. Okay. So let me start. Okay. Today's presentation. Okay. Basically lectures, my lecture slides. Okay. So I hope all of you are able to see my lecture slide.
Yes, sir.
Okay. So in my previous lecture, basically we had discussion about creep deformation. Okay. So we had spent okay ample amount of time to okay understand the what our understanding is there related to creep deformation. Creep deformation is a high temperature deformation phenomenon, which usually have considered under constant load or constant load or stress. Okay, and what we talking about only plastic deformation. In metals, what we talk about creep is basically related to plastic deformation, time dependent plastic deformation. So in polymers, we do talk about creep. There we talk about viscous flow, viscous flow behavior. Okay, viscoplasticity, viscoelasticity. Those things also come under creep deformations. Okay, so then apart from creep, regular creep test, we also have a creep rupture test and stress rupture test. So under creep rupture test, typically, if I want to know, time dependent plastic deformation at how much time is required to rupture the whole material. Okay, so one can use a Larson Miller parameter, which basically takes into account of temperature and time to rupture combination. So from that I can determine what is the stress requirement for a given Larson Miller parameter. What is the stress requirement below which the material will be safe, above which the material will be unsafe. Okay, at elevated temperatures. So we had this discussion. It's basically come under category of creep rupture. Okay. So then actually we had, I think, discussion about residual stresses. Okay. So there are actually three different type of stresses are available. Okay. We do see internal, what you say, internal stresses or residual stresses, which can present in a material, can be of three different types: type 1, type 2, type 3. Type 1 is basically come under category of macro stresses, and type 2 and type 3 come under category of micro stresses. Okay, so the length scale is going to vary. Okay, according to length scale, people have categorized that different types of residuals into type 1, type 2, type 3. Okay, so I think if you go to smaller and smaller length scales, we do see micro stresses are going to be there, like a dislocation, atomic related things. Okay, dislocation point defects can contribute to micro stresses in a material. It's called type 3. Type 2 basically is related to any kind of intragranular stresses between the if we take a polycrystalline material between the grain boundaries. Okay, along the grain boundaries, stresses will be present. Or so we also see, for example, reinforcement and matrix. We do also see at the interface, we do see some kind of stresses are going to develop. Okay, so because of the differences in the thermal coefficient of expansion can lead to thermal stresses across the interface between a reinforcement and matrix. Those come under category of type 2. So type 1 basically is a continuum kind of thing. Okay, or the material can have a change in dimensions in terms of that can lead to macro stress in a material.
Sir, are you changing the slides?
No, I think on the slide number 3. Am I right?
Because it is not changing.
But it was in the slide first only, sir. It was not.
First only. Okay, just 1 minute, I think. Just
Now it changed,
one
sir.
minute.
Now
One
it was
minute. Yeah. No. Just I did mistake. Some mistake. Okay. Just wait. I'm sorry. Thank you so much for that. I did small mistake. Okay. Mm. Okay. Are you able to see it now? Okay. Slide number 3. Okay.
Yes, sir. It is visible.
So basically, what?
No, sir. Actually, I'm not able to see.
Just 1 minute. I think it will take time for you. Okay. Just see.
Okay, sir.
No, just see that it will be okay. Usually takes time from depending on network connection. Are you able to see now? See slide 1 now. Okay, we had actually discussion on the creep deformation behavior of materials. Okay, then we had discussion about creep rupture behavior of material. So Larson Miller parameter is the important parameter which basically describes the time dependent temperature compensation parameter. Okay, so by taking a time and temperature, so one will get a Larson Miller parameter. For a given Larson Miller parameter, what is the stress we can apply to the material? Okay, so that the material can be safe or component can be safe. So for designing purpose, people use Larson Miller parameter. Okay, to understand effect of time and temperature on creep rupture or creep deformation of a material. So then we had a discussion of residual stresses. Okay, So there are three different types of stresses are present, can be present in a material as a residual stresses. So depending on length scales, small length scales, we talk about micro stresses. Okay, at a large length scales, we talk about macro stresses. Okay, again within micro stresses, we do see two different types: type 1, type 2, and type 3. The length scale slightly intermediate. Okay, intermediate one basically gives you type 2 stresses. Okay, so this is about all about residual stresses and creep deformation what we had in my previous lecture. So today's discussion is basically related to the next component is basically superplastic deformation. Superplastic deformation. So it basically simply called, the phenomenon is called superplasticity. Superplasticity. So when do you say a material is exhibiting superplasticity? Is basically called when certain materials, typically polycrystalline materials, exhibit very large uniform elongations, typically greater than 400%. Okay, then we call the phenomenon is called superplasticity. So certain class of materials typically exhibit very large uniform elongations. If it is the uniform elongation, if it is greater than 400%, we call it as a superplasticity phenomenon. So this phenomenon was first observed, scientifically reports. The scientific report was appeared, in the year 1934. It was mentioned, given by Pearson. He had taken a specimen like this, okay, which is made of bismuth and tin alloy. And when it was deformed at elevated temperature, when it was deformed under tension at elevated temperature, it exhibited very large elongation to failure. Okay, the specimen still has not failed. Okay, in order to take a photograph, he spiraled it. He spiraled the specimen after deformation. Okay, so with respect to original gauge length, he determined what is the percentage of elongation the specimen has experienced. Okay, is about 1950%. Okay, this was the first scientific report on superplasticity phenomenon. Okay, so people have observed this kind of phenomenon in various class of metals, metallic materials, intermetallic, ceramics, and composites. For example, here, lead tin alloy, lead having 62% tin, which is popular solder alloy. Okay, people have shown, for example, this group Ma and Langdon, what they showed, they demonstrated, this alloy, if we deform at a temperature around 413 Kelvin with a grain size around 10 micrometers, at a different strain rates, when it was deformed at different strain rates, at a particular strain rate, 2 in 10 4 minus 4 per second, the specimen has shown 7,550% of elongation. Okay, this is a record percentage of elongation that was reported in any class of materials. Okay, so this is a look at here what you are talking about. The elongation, so we are talking in terms of a 7,000%, greater than 7,000%. This is the record, largest elongations reported in the alloy is basically in lead tin alloy. Okay, so this behavior is not not only metals, people also observed having 1,000% of elongation even in ceramics. Okay, at a particular strain rate, when you deform at particular strain rate at particular temperature, some temperature. So people have shown in even ceramics do exhibit large elongations to failure when you deform under certain conditions with certain parameters. Okay, so this is actually became very popular. Okay, so the purpose, the advantage of having superplasticity, what is the advantage of having superplasticity? If a material exhibits superplasticity, what is the advantage?
Higher toughness, sir.
No, it's basically what happens. Okay, it's not the toughness thing. Okay, the stresses are very low. Okay, typically the stress will be very low. Though ductility very high, the stress will be very low. Okay. Any other? What is the advantage of having a superplastic phenomenon?
So forming is easy.
Forming is easy. Okay, so we can deform materials. Okay, we can form components. Okay, various components, complex components. Okay, very easily. Okay, so for example, some of the applications where superplasticity phenomenon has been used for making a single shaped component. Okay, like for example, a bicycle frame, single component, okay, by superplastic forming. Okay, some luxury cars. Okay, if you look at the luxury cars which use aluminum alloys, okay, so the whole body can be formed very easily by a material which exhibiting superplasticity. Okay. Even some of the luxury cars doors which use non-ferrous alloys, which are formed by using phenomena of superplasticity. Okay, even nowadays we are seeing wide chord fan blades, turbine blades, which are of a titanium alloys, made of titanium alloys, having a truss core structure, which basically uses diffusion bonding come superplastic forming. Okay, so complex shapes can be obtained from a material which exhibits superplasticity, okay, with a minimum load requirement. With very low load requirement, we can deform material. The tool varies very small, very low. Okay, the forming will be very easy. Okay. So that is a kind of where the superplastic phenomena is used. Okay. So what are the requirements for a material to exhibit superplasticity? What are the requirements for a material to exhibit superplasticity?
So fine grains, low strain
Fine,
rate,
low.
low strain rate,
Okay.
high temperature.
Mm-hmm. Okay. Anything else?
It should be free from cavities or defect.
Yeah, I think you are actually you listed all of them, almost. Okay, so basically superplasticity is considered as the elevated temperature behavior, elevated temperature phenomenon. So high temperature phenomenon. So if we have a high temperature, diffusional activities are going to be higher. Diffusional activities are going to be higher. So if you have good amount of diffusion, mass transport will be very easy. So that can get obtained very good large elongations. That's one requirement. High temperature is the one requirement. The second one, the most important one, is a relatively stable fine grain size. Relatively stable fine grain size. That is the second requirement. Okay, the third one, high strain rate sensitivity. The material should exhibit high strain rate sensitivity. Okay, the fourth one, cavitation, resistance to cavitation, resistance to cavitation. Okay, these are the four important requirements for a material to exhibit superplasticity. Okay, so these are actually if you're talking about elevated testing temperatures, typically greater than 0.5 times of melting point. Okay. Stable fine grain size. For metallic materials, the grain size should be less than 10 micrometers. For ceramics, the grain size must be less than 1 micrometer. Less than 1 micrometer. Okay. So the material should exhibit high strain rate sensitivity. The M value should be as high as possible. Okay, higher the strain rate sensitivity, we are going to see viscous flow, Newtonian viscous flow. Okay, close to viscous flow. Okay, M is equal to 1 means and its stress exponent is equal to 1. Okay, that means actually we can have a viscous flow. So that means resistance to flow localization. M is basically physical meaning of a physical significance. M is basically resistance to flow localization is going to increase if you have a material with high strain rate sensitivity. Okay, these are interrelated. Finer the grain size, we can see higher strain rate sensitivity. The strain rate sensitive material is going to be higher at elevated temperature in a fine grain materials. At the same time, the material should have a good resistance to cavitation. Okay, this internally we do see when you deform material at high temperatures, we do see materials, polycrystalline materials going to undergo cavitation. Okay, we should have increased resistance to cavitation. Okay, so these all are interrelated. Okay, these four parameters what you are talking about, these are all interrelated. Okay, any doubts here?
Sir, what do you mean by resistance to flow localization?
See, we talk about necking is the one of the problem during tensile testing. Am I right? When you deform a material,
Yes,
under
sir.
tensile conditions, what is the constraint? The maximum, is a necking. Okay, If the moment necking happens, so your non-uniform flow come into picture. The material is going to experience non-uniform flow. So it can fail at any point of time. If there is no necking, okay, then we can get a very large uniform elongation. Okay, so that is called flow localization. Necking is one of the flow localization phenomena, plastic instability phenomenon. Okay, if we can postpone necking, that can lead to large uniform elongations. Okay, I'll come to that slide. There is one slide.
Yes, sir,
Okay,
understood.
okay. Yeah, I'll come to this again. This particular thing. Okay, again. Yeah. Any more doubts here? Okay. See, high temperature. Okay, behavior. Okay, we talk about high temperature behavior at high homologous temperatures greater than 0.4, 0.5 times of melting point. We do use this kind of constitute equation, okay, which is almost similar to what we see in creep deformation. Okay, the strain rate, okay, steady state creep, okay, we have already this already bird, okay, bird Mukherjee Dawn equation, which basically tells strain rate, okay, is basically going to depend on stress, grain size, and temperature. Okay, there are constitutive parameters. 1 by m is nothing but a n stress exponent. M is a strain rate sensitivity, p is the inverse grain size exponent, q is a activation energy. So this okay, high temperature phenomenon at low stresses. At low stresses, if that material is deforming at low stresses, typically we use this kind of constitutive equation. So according to this equation, okay, if we refine the grain size, if you refine the grain size, what are the beneficial things? What we can see, if you
We
refine the
can
grain
go
size,
for high strain rate.
what can one can expect? Okay, finer the grain size, higher the strain rate. Okay, at, that's one thing. Anything else? Because I'm only refining grain size. Okay, at a particular strain rate, if you deform material, your stress requirement is going to increase or decrease with the refining grain size. If it,
Decrease.
okay, here are talking about sigma to, okay, if you constant strain rate, constant temperature. Now your sigma is proportional to, okay, d to the power of mp. Am I right? Proportional to d to the power of mp. That means, okay, m is a positive, okay, p is also will be positive value. Okay, finer the grain size, your stress requirement is going to come down at high temperatures. At high temperatures, the stress requirement is going to come down. That way you can deform material very easily if the material is finer grains, if your material has a fine grain size. Okay. So the other thing, okay, if you have a finer and finer grain size, okay, the effective diffusion path, okay, is going to be the length scale of a diffusion is going to be smaller. You can have a improved diffusivity because we have a large grain boundary area. Okay, the grain boundary is going to increase with refining the grain size, so that can lead to increased diffusivities in the materials. The flow can happen very easily if there is improved diffusivity, so that can lead to atomic movement can happen very nicely. So they can have an improved deformation. Okay, improved elongations. Okay, so these are the kind of, okay, beneficial things what we see. If you have a finer the grain size, more grain boundary area, so grain boundary mediated deformations can happen, like a grain boundary sliding can take place very easily. Higher amount of grain boundary sliding can be there if you have a finer grain size. So these are the kind of, okay, beneficial things what we see, okay, when you refine a grain size. Okay, so because of these, okay, kind of activities what we see, that can lead to large uniform elongations in fine grain size materials. Okay, however, okay, one of the major issues, if you refine a grain size, okay, can anybody say what could be the major problem if you refine the grain size?
The strength at the higher temperature will be less, sir.
Strength at the
Higher temperature side.
okay, yeah, that's what stress is going to come down.
Yes,
Okay,
sir.
anything else?
So there will be chances of formation of cavities in the grain boundaries.
Okay, but actually, yeah, it's high temperature. Okay, but actually, fine grain size might not be give you okay, easy cavities. That's what okay. Superplasticity basically, when you say superplasticity, resistance to cavities is going to be higher in those materials.
Sir, grain boundary sliding could occur if there are
Yeah,
more grain boundaries.
that's good. That's a good, no? So because for a superplasticity to have more grain bond sliding is good for it. Okay, more deformation can be induced. If I okay give you pure metal, if I give you pure metal, okay, one is 100 micron, one is actually 100 micron, other one is 1 micrometer. Okay, same metal, copper. If I give you, okay, if I heat it to high temperature, what happens?
Grain growth. Grain growth
Which
occurs.
which can undergo easy grain growth.
Fine grains.
Fine grain material.
Fine grains can undergo easy grain growth. Grain growth, the stability, thermal stability, is one of the major issues. If you go for a finer and finer grain size, thermal stability is one of the major concern. Okay, so because the driving force for grain growth is inversely proportional to curvature. Okay, the curvature basically we talk in terms of a grain size. Okay, so pure metals. Okay, even if you have a fine grain size, the moment when you take it to elevated temperatures, it is going to undergo grain growth. Then all your beneficial effects is going to be lost. Okay, that's why we do not see okay superplasticity in pure metals. Okay, superplasticity can be observed only when there is a stable grain structure. That's why I said we need to have a fine stable grain size. Okay, that can be obtained in case of a two-phase structures and quasi single phase with the particles. Okay, when they're precipitates. Okay, those okay like alloys and okay, which contain precipitates can only exhibit superplasticity, because we need to control the grain growth. You have to pin it down. Okay. So two-phase materials and quasi-single phase materials which contain precipitates, which can exhibit superplasticity phenomenon. Okay. Is it clear?
Yes, sir.
Sir, could you please explain the relation between D and sigma again? Just
Now,
that
if
part.
you maintain constant strain rate and constant temperature, all constant. Okay. Now only you have a sigma. If you send okay d to the power of minus at the other side, sigma to the power 1/m is proportional to d to the power of p. Okay, maintain all other constants. Okay, now except sigma and d. What happens? Sigma is basically proportional to d to the power of mp. Am I right?
Yes, sir.
Okay, this is constant. This is constant. Okay, take it one side, all of them. Okay, now I'm just want to have relationship between sigma and d. Sigma is proportional to d to the power of mp. M is actually positive strain rate sensitivity at high temperature. Typical materials exhibit positive strain rate sensitivity at high temperatures. And P is also okay positive value. Okay, so now sigma is directly basically we're talking about proportional to D. Okay, with some exponent. Finer the grain size, the exponent is a positive value. So finer the grain size, okay, lower the stress requirement. Okay, is it
Yes,
clear?
sir. Yes, sir.
Yeah.
Sir,
Any more
so
doubts?
the strain rate going up is not good, right? The
No, no. See,
point number two.
point number two, at a constant stress, okay, we have to maintain other parameters constant, okay, constant stress and constant temperature. Okay, fine grain size materials can deform even at high strain rates very easily. Okay, your strain rate, okay, that means your rate of deformation can be increased if you have a fine grain size for the same stress and same temperature.
Okay, okay, okay.
Okay, for the same okay stress and same temperature. Okay, if I have a fine grain, coarse grain, fine grain can material deform even at high strain rate as compared to low strain rate, as compared to coarse grain material. Okay, so that means the easy of rate of deformation okay can be increased if I have a fine grain size material. Okay, when I say strain rate here, let's talk about rate of deformation. Okay, is it clear? Any more doubts here? Okay, sorry, yeah, effect of strain rate sensitivity. Okay, so we said actually one of the requirements is a mm, strain rate sensitivity M value should be as high as possible. Higher the M value, we can go towards a viscous flow, easy okay, flow. Okay. So M, we know that okay, if I take okay stress at room temperature, typically M will be very small. Okay, so where do we take the power law equation between strain and the stress? Stress is basically epsilon to the power of n. N is a strain. Okay, strain hardening exponent. Okay. So, but once you go to high temperatures, okay, this basically okay, your strain hardening exponent is going to be almost zero. Okay, we'll be going to have strain rate okay, equation, power law equation. Okay, so there M is going to dominate than the N at high temperatures. So people usually that's why always represent okay sigma okay to take into account of strain and strain rate at a fixed temperature. At a fixed temperature, people usually represent sigma is okay proportional to strain and strain rate. Strain to the power of N, strain to the power of M. Okay. So if I okay take only okay this equation okay, if I convert into okay rate, so for example sigma can be written by P by A, load by area, load by area. Okay, if I take okay that one and it see what is change in area with time, change in area with time. If I just derivate it okay, I will get this kind of expression. Okay, using this expression, the initial power law expression, using this power law expression, okay, if I just replace sigma with the P by A, okay, and strain rate, okay, strain rate basically we are talking about change in strain, okay, d epsilon by dt. So epsilon change in strain, if you take it in terms of a, okay, we will get this expression. Okay, so this expression says, what does it says? Okay, change in area of a specimen. If you take a tensile specimen having an area, okay, the rate of change in area is basically going to vary okay in this fashion at a fixed load, at a fixed load with m, with increasing m. Okay, if you take a okay, there are m extreme cases you can take 0 and 1. Okay, if you take a m is equal to 1, m is equal to 1, what does it mean here? Your change in area with time, rate of change of area, if m is equal to 1,
Constant.
is a constant. Okay, it's independent of area, independent of your area of the specimen. That means actually it basically indicates that we are going to have a uniform flow behavior. If I take a glass, okay, I hope many of you might have seen glass blowing. Have you seen glass blowing? Anytime glass blowing, just okay,
Yes, sir.
nice. You can get nice shapes, okay. Or if you take a one, okay, cylindrical glass, okay, we can once you take it to high temperature, we can pull it like anything. We can make it a very thin, okay, fiber out of it. Okay, because of m is equal to 1. Okay, above okay glass transition temperature. Okay, if you deform a glass, if you pull the glass, it can flow like anything. Okay, you can get a very thin. Okay, if you take a thick rod, we can make a very thin okay wire out of it. Fiber, we can make a fiber, glass fiber out of it because m is equal to 1. Okay, they're actually independent of area. Okay, the rate of change is a constant. So higher the m value, okay, your rate of okay area change, that means reduction, how much you are changing, okay, the cross sectional area changing okay with time is going to be constant. That means constantly is going to change. That means there is no necking if m is equal to 1. Okay, so if higher the m value, okay, we can get a uniform elongation. Okay, the rate of uniform elongation is going to increase with increasing m value. Okay, so that's why like people, what people have observed by taking various materials combined and put it, okay, how okay the m okay and ductility, okay, person okay tensile ductility elongation to failure, okay, delta L by L naught, how it is varying. Okay, look at here. M value higher the M value, the tensile elongations are going to be higher. Both are on log scale. Okay, x and y, x and log scale. So this kind of relationship was found between strain rate sensitivity and tensile ductility. Okay, is it clear? Any doubts here?
Yes.
Okay, so when we talk about superplasticity, okay, it has some characteristic features. Okay, it will have some characteristics. Okay, for example, if I deform a material, okay, using tensile under tensile loading conditions, I deform the material. Okay, we'll get a stress strain curve at a different temperatures, different strain rates. Now fix the strain and temperature. Fix the strain. Okay, fix the strain and temperature. Okay, and if you see, okay, how stress is going to vary as a function of strain rate, as a function of strain rate. Okay, at a fixed strain, typically we take a 20, 30, 100%, whatever. Okay, we fix the strain and temperature. So typically, okay, the effect as a function of strain rate, the stress is going to vary like this, going to vary in a sigmoidal shape. Okay, and ductility or strain rate sensitivity, okay, ductility or strain rate sensitivity is going to be very like this as a function of strain rate. Okay, so if I take slope of this curve, okay, slope of the top curve, stress versus strain rate, what does it give you? Slope of stress versus, okay, the slope, okay, logarithmic scale. If I use a logarithmic scale, both of them, okay, what is the slope? What is its slope? See, stress is a log scale and strain rate is here. Okay, the typical stress variation will be like this. Okay, as a function of strain rate, the slope is nothing but strain rate sensitivity. If I get the strain rate sensitivity between these two values, we'll have like this. Okay, the strain rate sensitivity is going to vary like this. So depending on strain rate sensitivity, your ductility also is going to vary in a similar fashion, because the previous slide already showed, okay, M and, okay, delta L by L. Okay, so from this curve we can get a strain rate sensitivity. Then we can get shape of this curve like a bell shape. We do get a bell shaped curve, okay, between strain rate sensitivity and strain rate, or ductility versus strain rate. Okay, this is the characteristic behavior of superplastic materials. Okay, so there are three, okay, regions: region 1, region 2, and region 3. Okay, superplasticity, okay, regime is basically region 2. Okay, superplasticity window is basically region 2. Okay, this is basically low M value. The one, okay, region 1 is basically low M value. Similarly, region 3 also low M value. But region 2 will be having, okay, higher M value. Okay, that's why this region 2 is a superplasticity domain. Okay, if I deform material, okay, at the strain rates, okay, if I want to have maximum ductility, I need to deform material at this strain rate. Okay, at this, so that can give you this much stress per given strain. So this is a kind of domain, okay, where the material is going to show superplasticity behavior. Okay, is it clear? Any doubts here? Yeah. Are there any doubts? Okay, so typically, okay, the region 1, region 2, region 3, okay, strain rate sensitive. I hope I'm online. Am I right?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay. Yes. Okay. So the region 1, region 2, region 3, okay, if I see typical strain rates, okay, are less than 0.3 for region 1. Similarly, region 3 also less than 0.3. But region 2 will be having anywhere between 0.3 to 1. 0.3 to 1. Inverse grain size dependence. Okay, if I see, okay, the p value, okay, for region 1 is a 2 to 3. Okay, and it is a 0 to 1. It's almost independent of, okay, grain size. Region 3 is almost independent of a grain size. And the activation energies, okay, typically, okay, lattice activation, okay, lattice diffusion, grain boundary diffusion for the region 2, typically most of the cases, okay. And region 3 is, okay, will be close to lattice diffusion or pipe diffusion can also happen. Okay, so elongation to failure will be maximum in a region 2 because your M value is high. You can see higher elongation to failure. Okay, grain boundary sliding, okay, is going to take place, okay, at all strain rates, okay, at elevated temperatures. However, its contribution will be maximum. Grain boundary sliding contribution will be maximum in region 2, okay, as compared to region 1 and region 3. Okay, so we, if we deform material at this, okay, strain rate, and if we stop it and see the microstructure, we rarely see presence of dislocations, okay, in region 1. If I deform material, okay, at this strain rate and look at the under microstructure, the micro sample microstructure, okay, microstructure, we do see many dislocations. Okay, so in region 2 very few dislocations can be present, okay, in the material. Okay, so these are like a typical characteristics of a superplastic phenomenon. So any doubts here? Any doubts here? Is it clear? Okay, so typically this region 3 is associated with the dislocation creep mechanism. Okay, dislocation creep mechanism close to, because higher n values. Okay, m is low means n value is going to be higher. We do see a lot of dislocations, okay, in it under dislocation creep activity. Okay, so region 1, okay, can be a diffusion creep. Mostly will be associated with a diffusion creep mechanism. And the region 2, the dominant mechanism is a grain boundary sliding. The dominant mechanism is grain boundary sliding. Okay, if I take, okay, material is a zinc aluminum alloy, okay, when it was deformed, okay, at different strain rates, okay, so at a particular strain rate the material is going to see maximum tensile ductility. Okay, so one can establish, okay, this kind of curve, okay, what you have shown, okay, stress versus strain rate, we get a sigmoidal shape. And strain rate or a ductility, if you take a ductility measure, if you measure the ductility as a function of strain rate, we get a bell shape. Here the purpose of showing this slide is basically, okay, at a fixed grain size, if you deform material at this, okay, temperature, three different temperatures, okay, what is happening, okay, what is the effect of, okay, temperature, what is the effect of temperature, okay, on this shape of the superplastic curves. Okay, the superplastic curves, what you say in terms of a sigma versus strain rate and ductility versus strain rate. Okay, so with increasing temperature, okay, we do see, okay, the strain rate is shifting towards right, because diffusion activity is going to be more. So the, you can deform it even at high strain rates and large elongations can be obtained. Okay, so within this temperature window, okay, with increasing temperature, the rate of deformation can be, okay, it can be improved and large elongation can be obtained, okay, when you deform it at elevated temperature, higher temperatures. Okay, similarly, okay, if you look at here, uh, okay, for the same grain size, effect of temperature, okay, same effect of temperature with increasing temperature, with increasing temperature, typically stress is going to come down, stress value is going to come down. Okay, so this is a low temperature, intermediate temperature, high temperature, okay, at a given strain rate, okay, higher the temperature, lower the stress. Okay, so if I ask you to make a plot for different grain sizes, two different grain sizes, okay, one is actually assume that 1 micrometer, other one is the 10 micrometer, okay, how it is going to vary, just think about it. Okay, if I ask you to draw, okay, effect of a grain size on, okay, this superplastic curves, typical characteristic curves what we see. Okay, think about it, okay? Come back to, okay, I think I may ask you this question, okay? And you may have to draw and think about how, okay, what is the effect of grain size on this curves? How the, what kind of, how it's going to shift? Okay. Is it clear?
Yes,
Any
sir.
more? Yeah, okay. Just think about how effect of grain size on, okay, on shape of this curves, okay? Here I showed you only effect of a temperature. Okay, so I said, okay, one of the dominant, because with several mechanisms will happen, okay, when you deform material at high elevated temperature, any temperature, okay. So at high temperature, if you deform material, okay, the dominant mechanism for a material to exhibit superplasticity is a grain boundary sliding. Okay, for example, if you take a kind of, okay, material bicrystal, assume that I have a bicrystal, okay, with a boundary, now, okay, you put a scratch, some kind of scratch, very minute micro scratch has been placed here. Okay, if there is a grain boundary sliding, okay, what is meaning of grain boundary sliding? Basically, because of when you deform the material plastically, the shear component is going to act on the grains. Okay, across the boundary, we do see this kind of movement. The grains can actually each other slide each other. Okay, so initially I have a key like this marker. Okay, if a deformed material, assume that there is a grain boundary sliding, so we do see the marker is going to shift certain width. Okay, there's a some, okay, change in a this thing. Okay, this is basically is used, okay, the change in, okay, the sliding with respect to original grain size is taken as a grain boundary, okay, strain, grain boundary sliding strain. Okay, so in a, if we take a three-dimensional view of a, okay, grain structure, okay, three-dimensional, okay, simple assumption. So the grain bound is sliding, okay, strain to the total strain, the contribution of grain bound is sliding strain to the total strain is visually represented as a zeta. Okay, so here, okay, grain boundary sliding strain is basically calculated by taking a, okay, average, okay, with the change. Okay, for example, you have multiple grains. Assume that you have multiple grains in a polycrystal. You have so many grains with so many boundaries. Okay, so we know which are the boundaries contributed to the grain boundary sliding. Okay, we can know, okay, what is the change in, okay, change in the sliding width. Okay, that sliding with average sliding with respect to average grain size is basically taken as a strain due to grain boundary sliding. Okay, so in the region 2 of spot plastic deformation, okay, this, okay, the zeta value is going to be greater than 50%, greater than 50%. That means if, for example, 1000% of elongation, okay, is there, the material has experienced, okay, we can see actually more than 500% strain is coming from a grain boundary sliding activity. Okay, so I said if you have polycrystalline materials, typically what people do experimentally, okay, before deformation, put a scratch mark, okay, very micro crack will be placed, micro scratch will be placed, and after deformation and see, okay, okay, what kind, how much, okay, width change has taken place. So calculate average width change, and we know the average grain size of the material. So that can give you what is the amount of grain boundary sliding has taken place in the material. Okay, this is experimental way of estimating grain boundary sliding strain during plastic deformation of a material at elevated temperatures. Okay, so there are actually, okay, two different types of grain boundary sliding. There are two different types of grain boundary sliding activity mechanisms. Okay, so if we take polycrystalline material like this, okay, yeah, during deformation, okay, the grain boundary sliding is taking place. Okay, assume that grain boundary sliding is taking place. So this can become a like this, or can also become like this with strain. What is difference between, okay, A to C and A to E? Any idea? In both the cases, we have assumed that there is a grain boundary sliding. But there is a change, difference between A to C and A to E. What is the difference between A to E and A to C?
So coarse and fine grain size.
No, it
Is
is
that
same. I just started with the same grain size. Okay.
okay?
In one case, we are seeing this kind of shape change. In other case, we are not seeing a shape change of the grain.
So, sir, in second case, grain boundary sliding is dominant, and in the first
In
case,
both the
the
cases,
grains
okay.
are also
In both the cases,
deformed.
grain boundary sliding is there. The same amount of strain, okay. Your deformed material, both the cases, grain boundary sliding is there. Here, what you are seeing, okay, there is a shape change associated with the, okay, shape change associated with the grain. In the other case, we are not seeing any shape change. Almost, okay, more or less, okay, the initial shape of the grain is being retained. We are seeing elongated grains here. Here, we are not seeing such a elongated grain. Okay, so both the case, okay. So this, if okay, at the end of the deformation, superplastic deformation, if there is a shape change, okay, in the grain structure, then it is called, okay, lift sheets sliding. Lift sheets sliding, okay, if there is no shape change, but as I showed very large elongations, okay, that mechanism is called Rashinger sliding. Okay, so if you have a deform, initial grains are like this, if it is showing elongated grains, okay, but it has undergone sliding, okay, so this is called lift sheets sliding. If there is no shape change, but material has shown some amount of strain, significant of strain, that is called Rashinger sliding. Okay, so both the things can happen, okay, in materials, okay, but actually depending on, okay, what type of, okay, mechanism is basically accommodating the grain boundary sliding. Okay. Grain boundary sliding is happening in both the cases, but the accommodation mechanism, the type of accommodation mechanism is going to be different both the cases. Okay, when you go to high temperatures, okay, when you go to high temperatures, have and you have a particular grain size, okay, we may see dislocation creep and also diffusion creep. Okay, apart from grain boundary sliding, we may see either diffusion creep or diffusion, okay, dislocation creep. If diffusion creep accommodates your grain boundary sliding, that is called lift sheet sliding. If, okay, dislocation creep, okay, dislocation mechanism basically, okay, is basically accommodating grain boundary sliding, that is called Rashinger sliding. Okay, so for example, okay, if you take a grains like this, if there is a diffusion creep and sliding, now assume that there is a sliding has taken place. When there is a sliding, okay, sliding and diffusion, okay, has taken place here, for example, here, see, initially I have a grains like this, okay, hexagonal kind of shape. There is a diffusion creep because of diffusion, mass transfer take place, but it going to leave some cavities. But if there is a sliding activity, okay, that basically avoids the cavitation. Okay, even if you take, okay, these grains in an hexagonal style, when there is a grain bond sliding, okay, there is no shape change, but what happens, there will be voids going to be created. So that voids have to be, okay, will not be seen, okay, typically in superplastic materials won't be seen very easily, the voids formation, because there is a another accommodation, some another mechanism is going to accommodate mass transport, is going to take care of the mass transport. Okay, in one case we can see diffusion creep accommodation, other one is a dislocation creep accommodation. So when there is a grain bound sliding, apart from grain bound sliding, we may also see dislocation, okay, climb activity or diffusion creep activity, that basically, okay, minimizes the cavity formation in the material. Okay, if this grain bound sliding is accommodated by diffusion creep, okay, that mechanism is called lift sheet sliding. If grain boundary sliding is accommodated by dislocation creep, so that we can have a almost no cavities formation, that mechanism is called Rashinger sliding. Okay, so diffusion creep always lead to a shape change in the grain. Okay, dislocation creep accommodation lead to no, almost negligible shape change of the grain during superplastic deformation. Okay, is it clear about two different types of grain boundary sliding activities, what we can see in materials? Is it clear? Any doubts?
Sir, in one case, material is becoming ductile, and one case, material is showing stain hardening like that.
No, no. In both the cases, it's a superplasticity. Okay, there's no strain hardening. At high temperatures, we don't see any strain hardening. At high temperatures, negligible strain hardening will be there. Okay. In both the cases, okay, in both the cases, okay, materials are going to, okay, we are going to see large elongations at a low stresses. Okay. But how that large amount of strain is coming because of grain boundary sliding. That's a dominant mechanism. But that has to be accommodated with some other mechanism. Otherwise, it's going to leave you cavities. Okay, whenever there's a grain boundary sliding, okay, we do see wedge type of cavities. Okay, if there is a simultaneously some other mechanism also happens, like either diffusion creep or dislocation creep, that basically minimize the cavity formation. Okay. So in that process, okay, when diffusion creep is accommodating grain boundary sliding, that can lead to shape change of the grain. If dislocation creep accommodating, okay, is accommodating the grain boundary sliding, okay, then it can lead to no change or negligible change in a grain shape. Okay, so if the material is going to have a accommodation by dislocation creep, it typically exhibits large elongation, typically larger elongations than the diffusion creep accommodation. Okay. But in both the cases, even above 500%, okay, elongations can be seen, okay, by grain boundary sliding activity, but it has to be accommodated. If the grain boundary sliding is not accommodated, that can lead to cavity formations. Okay. So depending on initial grain size, if the grain size is finer, okay, the grain size is finer, typically subgrains are going to form. That is going to control, okay, control the grain boundary sliding cavity formation, okay, as compared to coarse grain materials. Okay, we need to have fine grains. Again, within that, okay, less than 10 micrometer grain size, if we talk about 1 micrometer, 10 micrometer, okay, 10 micrometer grain size can be, okay, can undergo, okay, this kind of, okay, grain boundary sliding with accommodation diffusion creep. 1 micrometer grain size will undergo dislocation, okay, creep accommodation of the grain boundary sliding. Okay, it's a grain size, initial grain size, what is present at the temperature. Okay, that makes a difference. What type of creep mechanism is going to accommodate the grain boundary sliding.
So that means without changing the grain shape, we are observing elongation.
Yeah, if there is a minimal, okay, shape change, we can get very large elongation. Okay, very large elongations. Okay, here we do see, okay, we do see some elongation of the grains, but at the same time, by the time it becomes elongated grains, already a lot of grain boundary sliding has taken place. That can lead to very large strains. So among these two accommodation mechanisms, dislocation creep mechanism can lead to larger strains than the diffusion creep accommodation.
Okay.
Okay. Yeah, but both the case, okay, once the moment we see grain body sliding, okay, the large fine grain, if we have 10 micrometer, you have so many grain boundaries that can lead to grain boundary sliding. Once there is a grain boundary, that means there is a strain. Okay, that strain, okay, going to be very high, okay, typically. But when the grain boundary sliding happens, okay, there will be a formation of wedge cracks. Those wedge cracks can be avoided. Okay, the formation of wedge cracks can be avoided. Okay, when there is a simultaneous deformation mechanism, either diffusion creep or a dislocation creep mechanism. Okay, if one of them happens, then your tendency for the cavitation is going to be minimal. Going to be minimum. Okay, if these two are not happening, either of them is not happening, then what happens? It is going to lead to failure. Okay. So that's where actually we are talking about. If you deform material at 0.3 times of melting point, same grain size. Okay, assume they have 1 micrometer grain size. One I deformed at 0.3 micrometer, 0.3 times of melting temperature. Okay, one I deformed at 0.7 times of melting point. Okay, what happens in 0.3 times of melting point case? Both the case grain board strength is there, but 0.3 times of when you deform material at a temperature 0.3 times of melting point, it is going to fail much earlier than the material, okay, deforming at a 0.7 times of melting point. Why? What was the reason? So I given two temperatures. Okay, one 0.3 times of melting point, other one is, okay, high temperature 0.7 times of melting point.
Maybe diffusion at a high
It's because
temperature.
diffusion, high temperature, we have a facilities of a diffusion. Once there is a diffusion, okay, your cavity formation is going to be controlled. Okay, mass transport can take place very easily by diffusion. Okay, so because of grain bond sliding, there is a discontinuity is going to happen in a polycrystalline materials. It has to be accommodated. If it doesn't accommodate, it's going to lead to failure. Okay, so that's what. Okay, even 1 micrometer grain size has a large grain bond area. Right? What happened? The problem actually here at low temperature, diffusion is low. Okay, that's whatever cavities or whatever discontinuity has been developed by grain bond sliding is not being accommodated at low temperature. At high temperature, it can be accommodated by diffusion or a dislocation because some kind of climbing can take place. At high temperature, you can see a climbing activities because higher the temperature, climb is easy or cross slip can be very easy. Those are high temperature phenomena. Okay, so that's where actually your temperature effect also come into picture. Okay, even if it's the grain size, fine grain size, but low temperature, high temperature, that is the issue. Okay, so we do see low ductility regimes in steels. Okay, and when you talk about deformed material at low, some intermediate temperatures, their grain bond is taking place, but there's no accommodation. That can lead to a cracking, failure of the component. Okay, once you go to high temperatures, either you can see dislocation activities like a climb and cross slips, okay, or diffusion activities can take place. So one of them can accommodate your sliding activity. So accordingly, we do see shape change in the crystals, grain structure. Okay. So after looking before deformation, we have a grain size. After deformation, plastic, superplastic deformation, if you look at grain structure, okay, if the aspect ratio if is very low, okay, the aspect ratio change. Initially, we have a aspect ratio 1, okay, initial grain size. So after plastic, superplastic deformation, if the aspect ratio is very small, okay, very small change, that means actually the material has undergone Rashinger sliding. If there's a large aspect ratio, okay, as developed, then we can say that grain bond sliding has taken place because of large, okay, that basically coming from a large, contributing to large amount of strains. At the same time, diffusion creep has taken place along with the grain bond sliding. Okay, is it clear?
Yes, sir.
So accordingly, okay, see if we know that subgrain structure is going to form when it form material at high temperatures. So we know the subgrain size is basically is related to 20 GB by sigma, typical for metallic materials. 20 GB by sigma. G is a shear modulus, B is a Burgers vector, C sigma is a stress. Okay, so we know for a particular material, if I deform it at temperature, once a temperature, I know what is the subgrain size it's going to form. Okay, at that temperature, if the grain size, grain size is less than equal to lambda, okay, that type of equation, constitute equation, which is used for describing grain boundary sliding is basically, look at here, a dgb by kt. Here d is a dgb, grain boundary sliding, grain boundary diffusion along grain boundary, and b by d square, grain size to power square. Okay, your p is equal to 2 and n is equal to 2, that means m is equal to 0.5, m is equal to 0.5 or n is equal to 2. Okay, so if the grain size of the material less than or equal to subgrain size, we do see grain boundary sliding equation, the constitutive equation for grain boundary sliding is described like this. So that means finite grain size we do talk about in terms of a grain boundary, diffusion through grain boundary, along grain boundary. Okay, and the dependency, the grain size dependency is going to be 2. If you have coarse grain size, whose size is greater than subgrain size, in that case, that means actually you will have slightly different constitutive equation for grain boundary sliding. Grain boundary sliding, because when you have coarse grains, typically we talk lattice diffusion. Okay, and we have a high n value is going to be higher, 0.3. Okay, around 0.33. Okay, 1 by 3. Okay, so we'll have a 0.33. M is going to be 0.33, n is equal to 3. Okay, it is equal to m is equal to 0.5. Okay. So this is a kind of typical superplastic. Most of super materials we need to have a fine grain size. Okay, should be close to equivalent to the subgrain size. Then typically we do see this kind of constitutive equation. So this kind of constitutive equation is basically, it is going to have a grain boundary sliding along with a dislocation creep. Okay, climbing activity can take place. That means grain boundary sliding is accommodation is going to be done by dislocation creep. In other case, okay, we are going to see, okay, some diffusion creep. Okay, coarse grains, typically coarse grains will undergo diffusion creep act. Okay, is going to accommodate the grain boundary sliding discontinuities. Okay, is it clear? Whatever I said, okay, these are kind of constitutive equations to describe about a grain boundary sliding activity.
So why did you say we'll go for case 1 and not case 2?
Because most superplastic materials, okay, will have, okay, our requirement, okay, is less than 10 micrometer grain size. Okay, if I calculate for a particular material, okay, at a particular stress, okay, where the superplastic stress is very low, okay, superplastic stress is very low, okay, so your lambda is going to be, subgrains is going to be, okay, coarser than 10 micrometers. Subgrain size is going to be coarser than 10 micrometer grain size at low stresses. Okay, so because if you talk about 1 micrometer grain, 2 micrometer, 5 micrometer grains structure, which basically follows this equation. Okay.
But I mean, in both the cases, your cavity is getting accommodated, right, by some or the other creep
Yes, yes,
mechanism. So
yes.
why case 1 is preferred over case 2?
No,
Right?
case 1 is preferred, not preferred. Both is going to happen. Okay, but if the grain size is finer than your subgrain size, okay, most of the metallic materials, if you take, okay, subgrain size typically falls around 10 micrometers. Okay, 10 to 20 micrometers comes. Okay, even actually, so grain bond sliding take place even coarse grain materials. The bottom one says grain bond sliding take place even in a, okay, in a coarse grain materials, but there actually the dependency of, okay, is going to vary. The grain size dependence and stress dependence is going to be different. Okay, when I say coarse and fine, with respect to subgrain size, with respect to subgrain size. Okay, now assume that I'm defining material fix, okay, at a stress of 50 MPa. Okay, I know shear modulus of material and shear modulus of Burgers vector. Then I can calculate what is the lambda value. Okay, it happened to be, okay, the grains, the subgrain size is going to be, okay, coarser than okay, superplastic material grain size. Okay, so grain bond sliding take place not only in fine grain, it can also happen in a coarse grain materials. Okay, superplastic materials should have a fine grain size. That when I say fine grain size, should be equivalent or less than typical subgrain size what it can develop. Okay, so this is actually mechanism which happens, grain bond sliding which happens at height, okay, in a coarse grain materials. Here, the grain bond sliding mechanism, the constitutive equation for grain bond sliding, which happens in a fine grain size materials, like a superplastic materials. Is it clear?
Yes, sir.
Okay. So what I want to say, the grain bond sliding can take place in both coarse and fine grain materials. Okay. Superplasticity can be observed only in fine grain materials. When I say fine grain, the grain size should be equivalent or less than subgrain size. In that case, we have to use this equation. Okay. In coarse grain materials, also we do see grain bond sliding, but there actually we have to use this kind of constitutive equation. Okay. Any doubts? Yeah. Are there any doubts?
So, sir, this constitutive equation tells us that which kind of creep mechanism will be used to accommodate in different grain size, right?
Not, it's not necessary to be, okay. Most of the times in coarse grain materials, diffusion creep is going to accommodate the grain bond sliding. Okay. So whatever said, lift sheets and passenger sliding, okay, both are going to both depending on, okay, grain size, depending on temperature, okay, the mechanism is going to change. Okay, the type of mechanism is going to the grain bond, within grain bond two mechanisms. This is actually will not say, okay, which is whether it is a lift sheet sliding or actually passenger sliding. So most of the times people actually fine grain size materials, okay, will experience this kind of grain bond sliding. So people call it a close to passenger sliding. Okay, this equation is close to passenger sliding. That this one actually close to, okay, lift sheet sliding. Okay. Applicable, maybe applicable to, okay, lift sheet sliding. This may be applicable to passenger sliding. So these are actually generic, okay, constitutive equations given, okay, based on a grain size. based on grain size. Whatever I mentioned previous two mechanisms, two different types of grain boundary slidings. Okay, the shape change, okay, the change in shape change, how it is basically coming up. Okay, if there is a diffusion creep, then we do see elongated grains. Okay. If there is not much shape change, that means actually okay, dislocation climb mechanism is basically accommodating the grain boundary. That's it. Okay, that ends there. Here actually the constitutive equations which it describes. So typically superplastic materials, okay, can under okay superplastic materials grain boundary sliding is going to be observed in fine grain size materials. The grain size will be finer than what we can talk about a subgrain size of a particular material. So in that case, most of the times people use this constitutive equation for superplastic grain boundary sliding in superplastic. In the bottom case, grain boundary sliding in coarse grain materials, it's not necessary to be a superplastic materials. Okay, so grain, because we know that we need to have minimum some grain size. Okay, then all we do is see a superplasticity. So these materials might not exhibit superplasticity. Okay. Okay, I think you have to. I think grain boundary sliding is a mechanism. Okay, it can happen. Okay, in materials when you talk about high temperatures, when you go to high temperatures. Okay, whenever as long as when there is a grain boundary, there is going to be grain boundary sliding. Okay, but in superplastic materials, the grain boundary sliding, okay, is going to happen along with the other mechanism, other accommodation mechanism. It can be a diffusion creep or a dislocation creep. Okay, is it clear?
So what are the benefits of having coarse subgrain size than the grain
No,
size?
no. It's basically, see, when you talk about, okay, that means dislocations. When you say subgrain means, what do you mean by subgrain? Dislocation cell structure has to form.
Yes.
Okay, then should become a, okay, annihilation should take place. Annihilation of the dislocation leave a some subboundaries like this. Okay, so if the subgrain size itself is greater than your grain size, that means there's no chance of a dislocation. Okay, pile up. Dislocation is not going to retain within a grain. Okay, there is no chance to, okay, because all dislocations, okay, there is no chance of having a dislocations within a grain. If the grain size is coarser, then we are basically facilitating formation of a subgrains. Okay, typically, okay, hard deformation, when you talk about hard deformation, okay, there we do see subgrain structure is going to develop. During superplastic deformation, we do not see subgrain structure formation because of fine grain size. Okay, the moment subgrains forms, which are of low angle boundary character. Okay, low angle boundary. Okay, subgrains have a low angle boundary, which have a low grain boundary sliding ability. Grain boundary sliding will be more only when there is a high angle character, and the Missouri angle greater than 15 degrees. Okay, we can see an increased grain boundary sliding activity. The moment when you see subgrains which have a low angle character, okay, there won't be any grain boundary sliding. Okay, that's where if we talk about directionally solidified material, okay, directionally solidified, we have a DS grain, okay, elongated coarse grains, and polycrystalline material. Okay, so when the grain boundary sliding activity is going to be controlled, okay, in a DS grade as compared to polycrystalline material, because those boundaries of most of the boundaries have a low angle boundary character. Okay, grain boundary sliding is also going to depend on misorientation angle of a boundaries. Higher the misorientation angle, easier of the grain boundary sliding. Okay.
Yes, sir.
Any more doubts? Yeah. Okay, so conventionally, okay, materials, okay, we talk about conventional superplastic materials. Typically, grain size will be 1 to 10 micrometers. Okay. So these grain sizes can be obtained by thermomechanical treatment. If you talk about, okay, some kind of, okay, rolling, annealing, some kind of playing with forging, kind of, okay, thermal mechanical treatments, we can get a grain size 1 to 10 micrometers. So what people have observed, okay, optimum superplastic conditions, okay, M value typically 0.3 to 0.5, okay, typically, okay, in conventional materials, and the temperature at which superplasticity has been observed, okay, in conventional materials is 0.6 to 0.9 times of melting point. The strain rates, okay, 10 power minus 4 to 10 power minus 3 per second. If you deform material at this rate, okay, at this temperature window, okay, which can exhibit strain rate sensitivity between 0.3 to 0.5, can exhibit superplasticity elongations. So far, I think we already mentioned record percent of elongation has been observed in a lead tin alloy at a temperature, look at here, 0.85 times of melting point, very high temperature. And the strain rate is very low. Okay, very low strain rate. One, actually, this behavior, okay, is observed, okay, high temperatures when the grain size is between 1 to 10 micrometers. And the strain rate is also very low. If the strain rate is very low, what does it mean? When a strain rate is low, okay, your production rate, okay, you cannot produce large amount of components. If I want to make a car body out of aluminum alloy, okay, if I want to make large number of, okay, components, one has to deform material at a very fast rate. But at high rates, at high strain rates, your M value is going to be low. Okay, cavitation can take place very easily. Okay, the dominant mechanism is going to be dislocation creep mechanism, dominant as compared to grain boundary sliding. So such a low strain rate, okay, that's one of the drawbacks of a superplasticity. Okay, we need to have a relatively high temperatures and low strain rates. High temperatures and low strain rates. Okay, so this is one of the major, okay, problem. And the other thing, what you are talking about, okay, record elongations have been observed in lead tin alloy, which is of, okay, no structural application. It's only for soldering. Okay, there's no structural application. Okay, only certain class of materials only exhibit superplasticity in a particular temperature window and a strain rates. Okay, so superplastic phenomena is used only for making components of a, okay, where we have a special requirement. Less number of components will be produced, around, okay, 1,000 components per year. Okay. So that kind of, okay, components only. That's why actually this phenomenon is used only for making a luxury car. Okay, luxury cars we see, which are produced, okay, only hundreds of thousands per year. Okay, there only this kind of phenomena is used. Okay, so people have shown, okay, I think there's a kind of, okay, kind of diagram schematically, percent of elongation as a function of strain rate. Okay, so our requirement is basically go towards higher strain rate from production point of view. If a material exhibits superplasticity at high strain rates, that is the best thing, okay, from production, okay, commercial point of view. So what people have said, okay, if we refine the grain size, okay, we can, okay, push the strain rate domain, okay, towards right, towards higher side. Okay, so this based on some different materials and their grain sizes, it was shown that, okay, if we refine the grain size, okay, we can actually get a, okay, high strain rate superplasticity. High strain rate superplasticity. Typically 10 power minus 2 is considered as, okay, above that, considered as a high strain rate superplasticity. That means we need to have a fine grain size. At the same time, this grain size has to be stable. It has to be thermally stable. Otherwise, again, okay, we know that, okay, it is going to grow like anything. Fine grain size can grow at rapid rate than a coarse grain size. So one has to have a stable grain size, and it has to be much finer. Then only I can get a high strain rate superplasticity. Okay, so it's a kind of, it was demonstrated, okay, by, I think, during my PhD. Okay, what we have taken a material, nickel, okay, nickel by electrodeposition, nickel some alloying element, sulfur as added. Okay, so it was shown, okay, the material can, okay, show very large elongations around 5,000% at a strain rate, okay, 10 power minus 1 per second, even at lower temperature, 500 degrees Celsius. Okay, with around 0.3 to 0.5 times of melting point and a high strain rate, we can see superplasticity in fine grain sized materials. The grain size at that temperature is about 0.5 micrometers, 500 nanometers. Okay, so that means if you can have a fine grain size, if you make the grain size stable at that, okay, temperature, we can get, okay, superplasticity in the large superplastic elongations at high strain rate. Okay, even at low temperatures also, you can lower the temperature also. Okay, because your diffusion activity is going to increase if you have a finer and finer grain size. So one can also lower the the deformation temperature. Okay, so these are come under category advanced for plastic metallic materials. Now there's a lot of work going on to get stable fine grain size materials so that we can deform material to large elongations at high strain rates. So I'll stop it here. This is the whole thing about the superplasticity. Okay. So if there are any doubts, please let me know. Any doubts here? Are there any doubts?
No, sir.
Okay. Okay. So I'll stop recording. Okay. If there are any doubts, okay, students can stay back. Okay. Others can leave the.
Hello.
Yes.
So we don't need to submit the PPT before 29th, right?